Welcome back, nerds, to the exciting conclusion of Unit 5.2.5's notes. There we go. I said it. Something like that. What are you looking at? She's eyeballing me. That's right. Anyway, you see all this stuff right here? We did that yesterday. All that stuff right there was stat, edit, put the list in, and then stat, calc, exponential regression, and remember when we stored it as y1? That's all that is. That's just telling you how to store your stuff. Okay. So we've already actually done that, and we're going to do it again. Yay! It says use a graphic calculator to find the exponential equation that includes these 2 points, and we're going to make our L1s our x's and L2 our y's. So graphic calculator, turn it on, stat, edit. You probably have stuff in your lists. Go ahead and clear it out. Remember, you go up to the L, you hit clear, enter, and that's how you clear that list. The x's are L1, so 3 and 7. The y's are L2, so 18.2 and 94.7. Just find the equation using the steps above. Basically what it means is do exponential regression, but also store it as y1. So we're going to do exponential regression, and we're going to store it as y1 at the same time. So stat, calc, and scroll down to exponential regression. If you're good at memorizing shortcuts, it's shortcut 0. But you don't have to know that. You can just scroll until you find it. Hit enter. Make sure your X list is L1, your Y list is L2. Make sure you have nothing in frequency list. That's for probability and stats. We're not doing that this year. Come down to store regression equation. Vars, Y vars, enter for function, enter for Y1. And it will now copy paste whatever function it's going to get you into your Y equals menu. Cool beans? Awesome. Go to calculate and hit enter. There it is. Now to write this down, I am going to have to use 3 decimals, but I need you to realize that even though it is a perfect regression model, perfect, when I write it down with only 3 decimals, it's no longer perfect. And that's one of the reasons why we stored it. That way we're letting the calculator carry around all those decimals for us to give us more exact results. .283-ish times 1.51-ish, that is actually 3 decimals because the third decimal is a 0, raised to the x. It tells us to sketch this graph, which I love this question because you just connect your dots using a curved graph. Don't touch the x-axis. There, we sketched it. I mean, it's whatever. It does say to label the y-intercept. Okay. Because it's a y equals b to the x, a times b to the x, excuse me, we know that a is our initial value, is our y-intercept. That's 5.283. We have been tasked with figuring out when it equals 50. So we're going to go to y equals, and we're going to use y1 as my purple graph, which we've already stored there, and y2 we're going to put in as 50, and we are going to use second trace intersect to figure out where our 2 graphs intersect. Remember, we're going to need to adjust our window. We have an image right here. Let's just use it as our window. So my x's look like it goes from like negative, I don't know what, negative 8 to positive 15. Whatever, and I'll just use 1s for the tick marks. But it's not going to get down to y equals 0, so I'll go from 0 up to 100, 110, whatever, it doesn't really matter. Just make sure you don't give it 100 tick marks. And then hit graph. And we'll have something similar to this on our screens. Second trace intersect is our friend. Second trace intersect is 5. Enter, enter. Get close to the answer. Hit enter one last time. Crud, I hit equals. Darn these fat fingers. Second trace intersect 0, 0. Or enter, enter, enter. There it is. About 5.451. Yes, ma'am. Mm-hmm. You didn't store it then. All right, let me have it. It should have stored the same way. Okay, so what you have to do is, okay, on the old school calculator, there's a way, we'll just pause the video while we try to figure this out. Epic failure, I couldn't figure out the calculator. Anyway, now let's talk about the natural base e. The number e, and I'm not high, you heard me right, the number e is a convenient choice for many exponential applications. This irrational number is used as the base in the function y equals e to the x, where e is a number that's around 2.718-ish. The graph of the natural exponential function, shown over here, has the same basic characteristics as y equals b to the x, where b is greater than 1 because, well, 2.718-ish is bigger than 1. So it's going to have the same y-intercept, 0, 1. It's going to be an always increasing function, and it's going to be always concave up. Cool with all that? Awesome. It's exponential growth, right? So even though it's not part of our notes, I want to show you how to relate it to the other type of exponential growth. Because this is also exponential growth, right? Yeah. What that tells me is that e can be written as 1 plus r. So r, my growth rate, is e minus 1, which is about 1.718-ish. So if someone asked you what the growth rate of e to the x was, you could say it's about 172%. And I'm only doing that because I think that AP is going to want you to be really good at manipulating your functions. It's the only reason why I'm doing it. Just nowhere in the notes. Okay? Alrighty. Now, E was not created. E was discovered. Ashley didn't like what I just said. Oh. And this is how, no, pi was discovered. No numbers are created, all numbers are discovered. It's not a contradiction. It's not controversial. Philosophy is garbage. That's why it's called a pseudoscience. Mathematics is a true science. Philosophy is a pseudoscience. But you don't think it's cool, like, that you can't help people's brains work? No, because they're not. We don't know how their brains work. It's all theory. No, it's a theory. Philosophy is a study of theories, but itself is a pseudoscience. I am talking about mathematics. Mathematics is a pure science, able to be proven true. The number e. Don't you rush me, woman. Okay. The number e is defined as the expression that you see below as n approaches infinity. This is supposed to say in calculus, and for some reason there was a space there. It's 1 plus 1 over n, quantity raised to the n, and the limit as n approaches infinity, it approaches the number e. What a weird thing to say, the number e. You mean how was it discovered? It was discovered exactly like this. Someone just being curious and saying, I wonder what happens if. Well, Leonard Euler is a nerd because it's often called Euler's number. He is the one that's credited with discovering it. Yes, Adi? Why would you do that? That's the real question. So the reason why you do something like this is more than one reason. One of the reasons is financial mathematics, because the formula for compound interest is right here. So if you were wondering what is the fastest compounding interest, so does it compound yearly, where n is 1, monthly, where n is 12, daily, where n is 365, half daily, every second? So what you do is you go, what if we allow the number of compounds per year to approach an infinite number of compounds per year? So you try to figure out what this becomes. And as it turns out, it becomes this number. Another way that it was useful to us was, from what I understand in my YouTubing, is that the natural log existed before E. So we had the natural log to deal with things, and they had to figure out what the inverse of that was. And as it turned, What would you use natural log for? I invite you to do your own Googling on the history of the natural log, because it was done. Anyway, what we're going to do for this is we're going to explore this number E, and we are going to allow n to equal these numbers and fill out this table. Parentheses, 1 plus 1 divided by 1,000 raised to 1,000. About, I don't know how many decimals we should go to. We're going to have to go to more than 3. I can tell you that. So sure, 5 sounds good. 2.71692. I don't feel like retyping this crap. So on this calculator, what I can do is scroll up, highlight that, hit enter, and it'll just paste it down for me. And then I can hit over, and I can just tack on another 0 to the exponent, hit enter again. Something went wrong. Thank you. To do that, you have to do insert, second insert 0, then hit enter. There we go, much better. So 5 decimals, 71815. Screw it, I'll just type it. Five decimals, 71827. I mean, it's growing. It's growing. And it's getting mad close to this number, isn't it? Because that to 5 decimals is 71828. A million, that's 6 zeros. (71828) to 5 decimals. If you're only looking at 5 decimals, it's equal to exactly E. But we can see that this number is a little bit less, just a little bit less. But it's correct to 5 decimals, 2.71828. We're going to pretend we did this on our graphing calculator. E is almost, it's a little bit more than 2.7. So here's y equals E. And our initial value, well, you can't plug in x equals 0, can you? Nope. You can't plug in x equals 0 because you can't divide by 0. What that means is that this function that we were evaluating here is actually asymptotic to x equals 0. Yeah, it means it's undefined there. It's a vertical asymptote because you can't divide by 0. No. It has a vertical asymptote and has a horizontal asymptote. As it turns out, E is its horizontal asymptote. And that graph looks like this. getting closer and closer and closer to y equals e. Yep. It'll never get there, but that is its limit. It's kind of cool. Well, you can't divide by 0, so it'll never touch that vertical asymptote. Why can't x be negative? It can be. But it's on the other side, though. Oh, you know why? Here's why. The exponential base can't be a negative number. And if x is the number like negative 0.1, what you have in here is negative 9 raised to the x, which is undefined. Okay, what's 1 divided by negative 0.1? What's 1 divided by negative 0.1? It's negative 10. What's 1 plus negative 10? Negative 9. Negative 9 raised to the negative 0.1 is an even root of a negative number, which is imaginary. That's why. Okay? Because you can't let the exponential base be negative. The exponential base can't be negative. Here, I'm going to pause the video. Okay, Desmos is done. Back on it. Here, notice this formula is exactly the same in those two different places. So what's really going on? Well, you're being shown that when you use e as your exponential base, what we have here is continuous growth or continuous decay. The way that it looks like AP is calling that is growing. It's a growing entity or a decaying entity. I don't know. Look, this is continuous. That's what I know. Continuous growth or continuous decay uses E. And you may have actually heard the formula called PERT, written like this. But instead of P, we're going to use A sub 0. So instead of saying principal amount, we say initial amount. And instead of saying R, they're using K. But it doesn't matter. It's the same thing. You know what really, really matters? What really matters is the sign on the value of K. Is K positive or is K negative? Because if K is positive, then it's continuous growth. And if K is negative, then it's continuous decay. And I'm actually going to squeeze a negative sign in here like this. And if you do it like that, then you can scribble this crapola out. And then just go, oh yeah, a positive K value is growth, a negative K value is decay. Ta-duh. Okay? I prefer to do it that way. I would rather know that if I see a negative up there, it's decay. Speaking of decay, the atmospheric pressure, P, on a commercial airline decreases as the plane height increases. So as height goes up, pressure decays. The pressure in millimeters of mercury, mmHg, the pressure is measured in millimeters of mercury, mmHg, and is related to the height h in kilometers above sea level using this formula. 760 e to the negative 0.145 h, where remember h is height in kilometers. It says, what is the pressure when the height is 4.5 kilometers, and just for funsies, that's about 3 miles. But we're going to stick to freedom units here. Okay. Oh wait, I mean not freedom units. The rest of the world units, commie units, and kidding. We're going to use metric because metric is what the rest of the world uses. There's only 3 nations in this entire world that use what we call standard. How full of ourselves we even call it standard. They are America, Myanmar, and a third one I don't remember. I don't remember. Yeah, we're just going to plug in 4.5 as h. So what is the pressure when our height is 4.5 kilometers? 760 e to the negative 0.145 times 45, or 4.5, excuse me. Whatever that number is, we're going to round it to 3 decimals. In case you don't know where E is, It's hiding right here above the ln key, so you're going to have to use your second button. Second ln. Negative 0.145 times 4.5 is 395.764 millimeters of mercury. Yep. Well, I mean, you know how to find equations using exponential regression, right? If they didn't give you the equation and they told you they wanted you to use an E-style equation and you had two pieces of data, you could set up the system of equations and solve for the unknowns, yes. Find the pressure when the airline reaches a height of 10 kilometers. Again, same thing. You're just going to plug in 10 this time. So the pressure at 10 kilometers, or about 6.2 miles, we expect it to be a smaller number because as we go up, pressure decreases. I don't feel like typing it all again, so I'm going to go up and highlight it, and where I had a 4.5, I'm going to type 10 and hit enter. There you go. 178.273. Millimeters of mercury. You know what I just realized? Is that when we say millibars, is that what we're talking about? When we say millibars for pressure, are they like literally bars on a, yeah, that's what this is. This is air pressure. What's that? Well, mercury but it's in a, I don't want to say thermometer, but back in the day it would be a glass tube and it had mercury in it. That's actually what thermometers were like also. And the pressure of a barometer would change the level of the mercury up and down. And so I'm wondering if the bars are representations of millimeters of the mercury in the tube. Yes? It's Iberia? Liberia? Oh, wow. How'd you know that? Oh, okay. So Liberia, Myanmar, and America. Interesting. Oh boy. Half-life revisited. So we already did half-life. I'm just going to remind you what the half-life general formula looked like. It was y equals initial amount, half-life is a multiplier, and we did t over n or k. I think they did k, where k and t had to be the same units, and k is the time, the length of a half-life. But half-life stuff, because it is exponential, can also be written in continuous format. I mean, in all reality, it is continuous. It is always constantly decaying and shooting protons off of it, right? So in all reality, this is the better way to model exponential decay. Notice that it says that k is less than 0 though, right? That means k is negative. So I'm going to do this, and I'm going to scribble out this part. I'm just going to put the negative sign there. You would have to know that the half-life is calculated, if you weren't told the half-life, using this formula. But you would have to be told k, where k is the decay rate. Now, if you're not told the decay rate, and instead you're told the half-life, you have to solve for k, the decay rate, to get it into your formulas. So, right as I pause the video, good question. Is this k negative? No, because in the decay formula, we put a negative in front of the k. K in this formula is either a growth factor or a decay factor, so to speak. When you're talking half-life terms, you need to know k, which we would call its decay rate, in order to figure out how long the half-life is. But a half-life is a positive unit of time, right? Well, since ln of 2 is a positive number, in order to get a positive here, you would need k to be a positive number. We put the negative sign in the formula because we know it's actually decaying. Okay? So no, it needed to be in the video. So yeah, if you're told half-life and you're not told your decay factor, decay rate, whatever you want to call it, for these E's, you have to use the half-life to solve for k because you might have noticed that this formula does not have a half-life in it. What this formula has is k. So you would need to be able to get k alone so you could substitute it in. So first, since k is in the bottom of a fraction, you'd multiply both sides by k. And what you would get is k times your half-life is ln 2. So how would you get k alone? No, get k. What'd you say? Yes, divide by half-life. So your decay rate or factor, I think it's called it's still called the decay rate, I believe. Anyway, k is calculated as ln 2 over whatever the length of the half-life is. Because HL, length of half-life, will be a number. Yes? If I was looking for k, yes. So let's just see. If I was talking about carbon 14, it has a half-life of 5,175 years. You do ln of 2, close your ln of 2, close your parentheses, divided by 5,175. So if you had to write the equation for carbon dating using E, you would be initial amount, whatever it is, times E raised to the negative, because it's decaying, 0.0001339 T. Yeah, that's scientific notation. It's not saying this number is negative. We put a negative in front because we know it's decaying. The half-life of a certain radioactive substance is 24 years. We're starting with 5.8 grams. We need to write a model. Well, again, remember, K is ln 2 over the length of the half-life. So our K value is the ln of 2 over 24. And I don't even want that as a number. I'm going to leave it as ln 2 divided by 24 because that will not be rounded when I type it on the calculator. The amount of radioactive material then would be the initial amount, E raised to the negative, because remember it's decaying, ln 2 over 24 times T. It says when will they be less than 1 gram remaining? All right, well, what we're going to do is we're going to figure out when 1 gram will be remaining and then say any time more than that. Cool with that? So when would 1 gram be remaining? What you're going to do is you're going to set up a system of equations and use second trace intersect. You're going to say 5.8 e to the negative ln 2 over 24 times t equals 1, where this is y1 and this is y2. And we're going to do second trace intersect to see where they intersect. Boink, turn my calculator on, y equals, I can clear that out now, 5.8 second e to the negative. I'm going to use a stack fraction, alpha y equals. If you don't have the ability to use stack fractions, put your ln 2 over 24 in its own set of parentheses. ln is on the bottom left-hand side, right above store. ln 2 over what? Right here. Look, I just pointed at it. Look, on store ln.
Oh, I thought it was one of the blue ones.
No, that's e, because it's the inverse of ln. y2 is going to be equal to 1. Now, I have no idea how many years this is going to take. But Radioactive stuff is pretty slow. So what do you think would be a good estimate for our window on the number of years? How big should our window get? No clue? 50? All right, window, 0 to 50. I don't want 50 tick marks. I'm going to go from 0 to 6 because my initial amount is 5.8. And hit graph. Let's see if 50 was enough. It's going to be close, but I don't know if it's going to be enough. Nope. Okay, we need a bigger window. Let's take our window to 100 then. If you don't like guessing and checking, you know a way we could have figured that out, how big the window needed to be? Say that she mouthed it, but you could have used the table to give you a hint at the size of the values. So if you had gone to second table, you would have seen that it takes a long time before he even gets below 3. So to get to 1 would have been a stretch. Anyway, we were here, second trace intersect. Second trace intersect. Yes, yes, scroll. Yes. So there's going to be 1 left after 60.865 years. So we say t needs to be greater than, because we want to have less than that, which means we have to dip below the red line. So that's to the right of the blinking cursor. So our time has to be greater than 60.865 years. Now, I already mentioned compound interest today. I already mentioned it. But here it is again. You should have already seen this formula before in Algebra 2. This is compound interest, where n is the number of times per year it compounds. What does the formula equal if it only compounds once per year? If it only compounds once per year, what do you end up with? If n is 1, you get this. It should look familiar. It's the exponential growth formula. That's if n is 1. Anyway, this formula, n represents the number of times per year it compounds. So if it compounds monthly, n is 12. So you got a 12 here and a 12 up here. If it compounds quarterly, n is 4. You've got a 4 here and a 4 there. If it compounds weekly, n is 52. Daily, 365. Bi-weekly, 26. Bi-monthly, 6. Things like, 24, excuse me. And there's a lot of different things. You just have to pay attention to them. Okay? But I will tell you that, remember, if you allow 1 plus r over n to the n, well, if r was 1, go to infinity, you get e. Remember, continuously compounding is the fastest compounding. Suppose you win a writer's competition at the start of 9th grade, and they deposited $5,000 in an account that pays 6.25% annual interest compounded continuously. There you go. That's how you know to use E. How much will be in the account when you enter college 4 years later? All you have to do is fill out the formula. So here you go. A of t is your initial amount, 5,000. E raised to the, it's growth. So is r positive or negative? Positive. And what am I going to write for r? There it is, 0.0625. You never use the percentage. Times t. And our t is 4. Okay. Remember, for money, it's 2 decimals because pennies, So we're going to round to the nearest penny. 5, 1, 2, 3, second e to the 0.065 times 4. And hit enter. Okay, about $6,420.13. Boom. That's it. That was the whole unit, you nerds.